I would always start with the chemical reaction, because how do you know what is happening if you don't have the reaction? Yeah. So I think whatever you're doing, if you have a calculation and if you have a chemical reaction taking place and you have either to describe the observations or like calculating something, I would write that down. Okay, that was easier, because if you're lucky and if you forget about the equation, then well, maybe the ratio didn't matter. But if it does, which it could, I mean, it's a 5-mark calculation, so there might be ratio there, if not better, but you never know. The balance equation, it's always the starting point. So I would do that. If you're given weird compounds, you will have the formula. So then you just need to work out the products, okay, and the balancing. Okay, but in this case, I mean, I would do it just for habits, because it's 1-to-1 ratio and nothing happens. But this still helps us visualizing what's happening, that we have this amount, so 44 centimeters cube of hydrochloric acid mixed with 40 centimeters cube of sodium hydroxide to give this nice solution of 84 centimeters cube. I wanted to think it like that because you like visualize that you literally have 2 flasks and you put them together, a neutralization reaction takes place, and then you measure the pH. But in this case, we can calculate the pH, but we need to think about what is the pH determined, because they don't go perfectly to completion. I mean, it goes to completion, the reaction, but they probably don't neutralize themselves completely because we have different volumes and different concentrations. So it could be that one of them is in excess. Another way to think about it is like the calculations that you do when you have to find the maximum mass of something. You always find the moles of the limiting reactant. You do it with like just because they tell you already what's in excess. So whichever calculations or reaction you look at and you have some values, think about limiting excess. Sometimes you are told, sometimes you need to find it. And it's very simple mole calculation. So we can find the moles for both, keeping in mind converting the volumes and so on. I would find the moles of H plus. I'm going to write it like this to make it a little bit more relevant to the topic, and moles of OH minus. It's okay to do it like this because we know that H plus dissociate into, HCl dissociate into H plus and Cl minus, while the sodium hydroxide dissociate into sodium plus and hydroxide ion. And those are the ones that are relevant, H plus and OH minus. Okay, that's the important thing. And that's what determines at the end the pH. That's why we can write it like this. If we had diprotic acid or a base with a 2-hydroxide, then we would need to consider the ratio. That's when I say writing down the formula can be really helpful. Anyway, for the values, to make it nice and quick, the moles of H plus is 0.0088 moles, and the hydroxide is 0.02, doing the right conversion of the volumes and so on. We can clearly see that the moles of hydroxide will be in excess, but we need to think that some of this hydroxide has gone here in forming water, which means that not all of it will contribute to the pH, just the one in excess. That's why the next step, why did I leave so much space? I'm just going to move around. It would be to find the moles of the hydroxide in excess, which would be equal to the difference between these two numbers. So that's 0.0112 moles. I wouldn't mind the decimals now. I'd rather do using in this case, it says 2 decimal places, or a significant figure at the very end. So here, use as many decimals as you can. I mean, if you have a super long number, maybe just keep 4 or 5. Okay, so it's important for the pH, as it can give a very slight different value. We have the moles of hydroxide. We know that we always do the pH calculations with the concentration. So we need to think that this is we need to think about the new volume, because of course these moles are now mixed in 84 centimeters cube. So we divide these moles by the new volume, which gives us 0.1333. Again, I don't mind the decimals now. Okay, so we need to think about all of these things, but so far it's just a limiting reactant calculation. Actually, of course, we need to get to the concentration. Noticing that we are given the Kw and it's a hydroxide that is in excess, we need to find the pH. So we do we use the KW, remembering that KW is concentration of H plus times the concentration of OH minus. So I'm doing the rearrangement just because it's better if you have the equations down, whenever you have to do some rearrangement or just to keep track of everything. When there are so many steps, it is useful to write down also the equations, so you know exactly always where to look, what to find, and it makes it a bit clearer overall to understand. So plugging in the values, 1 times 10 to the minus 14 divided by that 0.1333, we get 7.5 times 10 to the minus 14. And then we just do the negative logarithm of that to get the pH of 13.12, okay? So let's be picky with the decimals. So keep them as many as possible till the end and then do the last rearrangement. So remember, a good habit of any calculation is that once you've done it, look back at the question to check if you've missed any step or if you are required to specify the decimal places or the significant figures, okay?